When words, graphs, and equations are used to represent the motion of an object, the connection between these representations and the motion of the object itself are not obvious to the learners, but very easy for an educator to assume that the learners will just pick it up. The learners have to go through a process of making those relationships. For example, it is far too easy to see a graph as a pictorial representation of motion instead of a representation of a relationship in the motion. These graphs all represent the same motion, but different relationships within that motion. Each one is true, but the shapes are different and definitely cannot be understood as pictures. By the end of the lesson, the learners should be able to determine whether there's a non-zero resultant force acting on an object by observation of the movement of that object, and see how vectors can effectively be used in representing forces and working out their combined effect. Today's lesson will be in two parts. The first part will teach the learners that force has to be applied to an object to get it to move, because there's a frictional force opposing the applied force. And in the second part, the lesson will show the learners that when an object is static, it is the result of forces acting on that object. For the first part of the lesson, the educator will demonstrate frictional force and its impact on applied force.
Push this chair. Just push it. Okay, come back again. Just start from the initial point. Just push it again. My question is, Theophilus applied force. Then after a certain time, was his force, the force that he initially applied, what did he carry on pushing with that force? My point is, I'm trying to raise that when an object, starting from rest, it has to first overcome friction. And then, once you start pushing, you have to put a lot of strain, right? After that, you can even push it with your finger because you already overcome friction. Do you understand me? I have a book which is on a table. And this book here, there's a force which is applied to this book, and the book is pushed. What happens to the book after a certain interval? I will redo it again. Here's the book, it is pushed. What happens? It moves and stops. What causes the book to stop?
It's the friction force.
It is the friction force. It is the force which is counteracting the applied force. Remember, this surface is not that smooth. What happens now if I take this book and reduce the friction area, place my book on marbles. Place my book on marbles and then just touch it. What happens to the book? Does it stop? No, just imagine this book wasn't in its way. Right. Did it? It continued moving. Now, we can result this by representing Newton's law. Which law is it?
Newton's second.
What does it state?
It said if objects, when the objects are moving with a constant speed and the set is applied by a negative force.
An object will continue with its constant or uniform velocity unless it is counteracted by a resultant force. Do you all agree on that? The need to push comes from the opposing frictional force. Once we have overcome this friction force, then your object moves at a constant velocity. Now, Newton formulated or came with a formula.
The educator now demonstrates to the learners Newton's formula, that is force equals mass times acceleration, to calculate the acceleration of the book across the table.
This will cancel with this, then I'm left with acceleration is equals to 15 divided by 0.0008, which is equals to?
18,750.
18,750
750 meters per second squared.
This part of the lesson shows the balance of three forces acting on a single point.
Just gonna place this on this side here. I want one volunteer just to keep this still fixed. This one, you just hold it down. No, not on top, just hold the string down. And I need another volunteer. Two volunteers to come and pull this. Okay, and then we're gonna compare this to the reading we're gonna get this side. Okay. Okay, let's leave everything at 0. Okay, now pull now. Yeah, until you reach the equal magnitude. Just take it as 3. Leave it at 3. Leave it at 3 before it snaps, right? 3, 3. What is the reading on this side?
6.
How can you convert? It's 6 on this side. And then, and this side, yeah?
It's 3.
It's 3. But how many spring balance we have there on the other side?
2.
We have 2. And each is pulling at a magnitude of 3. So then we can conclude now. Look at it, they're all pulling in a straight line, but in different direction. The reading of the equilibrium must be equal to the sum of these 2 spring balances, right? Now let's see now what happens if I increase the angle between them. Remember, this now is being pulled in a straight line. What happens if I increase? Now I want you to open up, increase it, increase the angle, okay, increase it. I'm increasing this angle now, theta, but you're still pulling at 3, 3. What happens to my magnitude? My equilibrium? It is decreasing. I want you to increase the angle until you get a line which is perpendicular to the increase. What happens to my? They are still pulling at 3. If this angle, if these are pulled in the opposite direction, does that have any effect? What is my reading on the spring balance? Number 3, 0. But yeah, they are still reading on these, which they are pulling at equal magnitude at 3. We can conclude now, if I increase the angles between my 2 forces, my third force will decrease. Okay, over mass M, and this theta which has been formed on this, theta has been formed on this. Now, this force will be acting downwards because of weight, right? This tension will be being pulled upwards, and this one will be pulling upwards. What I have here now with me, I have a force F, which is pulled on this side. I'll call it F1. And I have, which I'll call F2. Then I'll call this F3. Because my object is not moving in this case stationary, that means now the sum of F2 and F2 will result in what? F3. Now this, I know now, in constructing this, I know there's a force which acts upwards, which is my resultant force, isn't it? Which is my resultant force. Then I will bring this as it is, right? And then making this parallel to this, then I have my triangle. In front of you, you have a piece of paper, an exercise. Working in pairs again. Please do 1 and 2. Sum up everything we started.
At the end of the lesson, the educator ties the 2 aspects of the lesson together with a brief summary.
Lastly, and we finalize by focusing on 3 forces acting on 1 point. And we constructed vector diagrams to represent Those three forces can be represented in the form of a diagram, or triangular method, or parallelogram. So now, for homework, I want you to complete all the work that wasn't done, that we did not able to complete during this lesson.
Hello viewers at home, we have just watched a lesson on physics and would like to talk about this lesson. At the studio today we have Mike,
Hi, Tembi.
Dale,
Hi, Timby.
and Andrew.
Hi, Tembi.
There was a small class of boys, and there is always a perception that physics is mainly a boys' subject.
Tembi, what I think is it really is unfortunate that you have a class like that. It was a small class, yes. The ratio of learners to teachers in most of the schools in Gauteng, Limpopo, and so on throughout the country, actually, you have an average of 1 to about 30. Now, for every one teacher, you have 30 learners. It can get, in some cases, it gets much higher. If you're in grade 10, you could be looking at up to 50, 57 learners. So I think here we are very, very lucky to have such a small class. And of course, you have one-to-one interaction, and it makes it much easier to manage the class as such, But I think the fact that you only have boys reinforces the misconception that science is for boys, and I think that's it, because we need to, as a country, schools, we need to encourage more girl learners, because that also is a big need and requirement for our country. Because the more girls we can get, the better, and also the more we can deal with all these other negative attitudes about science being for the few, science being for the so-called elite class, the better, because these attitudes go a long way in influencing how learners actually learn in the achievement in class.
Now let's get into the actual lesson. The teacher made use of a lot of practical examples. How effective were those in the teaching of motion?
Timby, I thought in watching what he was doing was how much it is that our theory influences what we see. He knew what he wanted to see in those demonstrations, but I didn't always know what he was getting at. When the chair was pushed across the floor, I just heard a chair making a lot of noise. I didn't register that it was taking some time to get going because of the frictional force initially, that it was accelerating in the first part of the motion. And I thought that demonstration with the marbles was lovely because the book rolled very nicely. But because the area in which the marbles was so small, the book came to a halt almost immediately. Now, he then asked the learners, what did you see? They saw two things. They saw the book going, and then they saw it stopping. And he was actually only focusing on the going. So I think what we observe in those situations depends on what our understanding of the physics is. They say there's no such thing as an observation. All observations are actually inferences, because you're judging what you see through the lens of what you already know.
So in the case of the marbles and the desk that the teacher used, what sort of advice would you give to the teacher?
I think you need to give the students a hint that you're looking at the book before it hits the edge. What did we notice before it got to the edge?
Okay.
Yes, I think that the mistake that the teacher made was that he basically answered his own question without giving the class sufficient time to think it out for themselves. I think he should have asked the class to look carefully at the demonstration. Perhaps could have repeated it a number of times, and then gone around the class trying to elicit various views, and they could have had a debate about it. So he could have made much more use of what was potentially a very good demonstration failed because he was in too much of a rush to get to the decision that, or the conclusion that he wanted to get to, as Dale has said.
The other thing that the teacher was good at was actually trying to get some responses from learners through questioning. What do you think about his questioning skill at this point in time?
Yes, I think it was good. I mean, he made an attempt there at asking the learners questions, and trying to manage the learning environment. He set up the experiments, learners were observing things, and they were asked questions. he's in control of the class. That's fantastic. But I think we must say that the response time he gave the learners was very short. And I want to go back to what Dale said. You know, a lot of times he was expecting them to see what he wanted them to see, and they may not necessarily have picked up on those issues. And I think that is the crux of the matter in this case. And that needs to be looked again and corrected in this particular lesson. Excellent way of managing the classes. Questions, there were some direct questions. He used probing. I'd have liked to see him use probing a bit more. You know, and as Mike also pointed out, actually engage the learners to discuss amongst themselves. You see, Tim, because peer learning is also something that is very, very powerful. And I think he actually almost forgot about peer learning. And in a way was almost stage managing the thing and was getting too involved and not giving them a chance to discuss things and analyze things. Sorry, Dale, you were saying?
He did give them some pair work at the end.
He did,
and that was nice. I think.
Yeah, that was great. Yes.
I think that one of the problems in terms of asking questions with such a small class is your questions don't go anywhere because there's more pressure on the learners in a small class. And I found that it's actually quite difficult to work with a small class. I prefer a larger class because there's more chance of somebody in the class coming up with answers to questions. And with a small group, you can end up answering your own questions.
Yes, there is more interaction with the larger groups.
But I think that, for me, very beautifully sets the stage to actually engage in probing, you know, to see just what misconceptions are there and how prevalent those misconceptions are. I think it's a fantastic environment to detect misconceptions and also to deal with them because the class is small. But I mean, I do agree with my colleagues that there's also a downside to the class being too small.
You know, one very simple demonstration he could have done was simply to bring a soccer ball into the classroom and get them to roll it along the floor, and then ask questions about, you know, why has the soccer ball proceeded a lot further than the book that was pushed, just to get the point across that in the case of the ball, one was dealing with a much smaller frictional force, and so you're getting closer to the limit where friction is going to disappear, and then your once the ball is got into motion, it will continue in a straight line at constant velocity, which is Newton 1, which I think he was obviously trying to get to.
Having said that, Mike, the teacher also brought a lot of resources, including the overhead projector. How do you think those resources were used? Were they effectively used? The overhead projector and the marbles and all the things he brought into the classroom.
He had an unusual way of writing on the overhead, writing on it so that the image was sideways on the wall, on the screen. But the learners seemed to cope with that. That's obviously what they're used to. And I think that there's tremendous advantage in building up a picture gradually, as he was doing on the overhead, so that learners can see where the different parts of the picture have come from.
Any other thing that you think was of interest in the lesson?
He could have done a number of other things, like bringing in a ball, perhaps pendulum, depending on how he's going to use it. You know, he could have done a few other things just to reinforce some of these concepts. And I also think, you know, we should try and make the effort to use trolleys, you know, in the normal runway. You do get friction-free runways that you can get it very cost-effectively. And I know there's always a cost factor to consider because there's limited funds around. But I think it's just sad to deny learners the opportunity to actually do these things under more workable and in a more workable environment.
I think it was good, though, that he raised the whole issue of friction, because strictly speaking, the syllabus doesn't talk about friction, and our everyday experiences are full of friction, and that's why, in fact, Newton's laws seem very. People don't really believe them. They look at them and they seem simple enough, but people don't really believe that Newton's laws are true because in their everyday life they've always got friction to contend with. And I think we also saw that with the teacher talking about friction being overcome at the beginning of the lesson there. And in fact, it's never completely overcome. You can get situations like with the ball, the rolling ball, where the effects of friction are negligible, but it's never actually overcome. And that's why we have this resistance to really believing what Newton's laws are. I did an interesting exercise with some students where I got them to answer some questions after they told me that they knew about Newton's laws and that, yes, they thought they were right. And in actually answering the questions, they didn't use them. They use their own alternative ideas about things. And when I said, no, but Newton's laws apply here, some of them really argued with me and thought I was talking nonsense. So I think it's not as simple as it seems.
Yeah. I also picked up some language issue towards the end when a learner was asking another learner, but in the mother tongue, saying, the teacher is saying this line is straight, but this line is not straight. You agree with the teacher, but the teacher did not pick up that one. So also the learners themselves were in a position to share, although the other learner couldn't get the response. So maybe if the teacher has to look at some of the questions that come out from the learner, that would be useful. Towards the end, the teacher gave some homework for learners to go and do some of the activities at home. What do you think about the strategy of giving learners to do homework when they are home?
Well, at this level and in this particular topic, it's absolutely essential. I think that it's through practice that one slowly gets to have a better understanding of what force is and how forces balance. So certainly I think there always comes a time when the talking must stop and the doing must start, and so the homework was a good idea, and I would endorse that.
Is it common in our classes that you usually observe, or in schools that you visit, that teachers give homeworks to learners?
I find, Tembi, with my own experience, tells me that the majority of schools do. But I've had an opportunity to talk with some teachers who don't actually do that. And it's interesting, the reasons that came up. But one that always came up was that homework is not given because learners don't do the homework. So what they do is they structure the school time such that there's an hour or two after school. They keep the learners in so that they do their homework, they do work and so on. Especially in rural areas where learners have long ways to travel and so on. It's a bit problematic sometimes for them to do homework. So, they're given a chance at the school to do the homework. But I think it's a fantastic way to conclude a lesson, because it will reinforce whatever the learners have learned. And it gives the teacher an opportunity when they actually look at how the homework was done to see where the problems are and actually to remedy those.
And also that teacher is very lucky because there are very few learners, so it would be easy to check on their homework as well. Is there anything that you'd like to talk about that was of interest to you?
Temi, just on a totally trivial point, we started off by regretting that there were no females in that class, and I think it was just 2 days ago, I was looking at a list of the Nobel Prize winners for physics from 1901 to, I think it was, to 1992, and other than Marie Curie, who won or shared the prize in 1904, subject to correction, there were no other ladies' names whatsoever. So that's just a little anecdote.
Okay, so it means therefore we as women have a challenge.
Yes, very much so.
A big challenge, so that we should be starting now to be saying to our learners they should go and do physics. Well, ladies and gentlemen, that's all we had for today. Thank you, Mike.
My pleasure.
Thank you, Dale. Thank you, Andrew. Thank you, viewers at home, for watching this lesson. We'll see you next time. Bye-bye.